Hey everybody, this is Mr. Charnetsky, and this is Unit 4, Lesson 5, Spheres and Compound Solids. So this is our last lesson in this unit, and this is the last topic we're going to talk about in 3D geometry. Now we're going to start with surface area. Now previously, all the other solids that I have gone over, I've taken the solid and sort of unwrapped it and shown you how the surface area formula is related to that. It's exceedingly difficult to do that with a sphere. In fact, you really can't theoretically unwrap a sphere into a two-dimensional object. It's just not possible. You could try and kind of slice, little wedges and so forth, and that's kind of how you manufacture like spheres and into like shapes like basketballs and things like that. But even these shapes are not exactly going to be 100% flat. So you really can't unwrap a sphere the way you can, flatten out a box or a pyramid or cylinder, any of those. It just doesn't work for a sphere. You could try it with, unwrapping an orange, and you can tear it enough so that you could kind of get it to lay flat, but mathematically it just doesn't quite work out. And this is actually a real problem when you're trying to take, for example, make a map of the globe. You end up with stretched out areas. The tops and bottoms tend to be stretched out and misrepresented, while the center parts are a little bit more to scale. The actual surface area formula is pretty simple. You only need one thing to input, and that's the radius. In this case, our radius is 9 centimeters. So we go ahead and plug that in. Surface area is 4 pi times 9 squared, so that would be 4 pi times 81, and 4 times 81 is 324. Oops. So 324 pi as an exact answer. Excuse me. Times pi. Make sure I got that right. Different calculator. Okay. So if I do 4 times 9 squared, yes, we do, and get 324 times pi. There we get 1017.9 approximately. And our units are centimeters squared. Excuse me. For volume, our formula is 4/3 pi r cubed. And for this particular sphere, they gave us a diameter. So in order to find the radius, we would have to cut that in half. So the radius would actually be 15.1 centimeters. So we'll go ahead and plug that into our volume. So 15.1 raised to the third power is 3442. Should be about 3443. And figure out the 4/3 part, so I'd multiply by 4 and then divide by 3. So times times 4 divided by 3 gives us 4590.6. Pi, which I'll then multiply out. Oops. There we go. And we get 14,421.8. And this would be centimeters cubed, or cubic centimeters. And this is an approximation because we rounded. You can do this whole thing at once if you know how to operate a calculator. You can put in the whole formula all at once and save yourself a little bit of time. If you have more of a graphing calculator like this, we can go ahead and do 4/3 times pi. Oops. Times. Give me a second button. There we go. Times. It's our radius 15.1. 15.1 to the third power. We should get the exact same answer, which we do. So, if you can get the entire formula in to get an approximation, you can do that as a faster step. Okay. Alright, so that's surface area and volume of spheres. Next thing we want to look at are the volume of compound shapes. So we have here in the orange shape here, we have really, in this silo shape thing, we really have a cylinder topped with half of a sphere, or a hemisphere. So we're really, what we're going to do is we're going to find the volume of the two parts, the cylinder down here, and then the hemisphere as the second part. So the area, or sorry, the volume of a cylinder equals pi r squared h, in this case our radius. Let's see if I can show you here. Radius is going to be half of that 10, so 5. So we'll plug that in, pi 5 squared. Our height is 6. So 5 squared is 25 times 6 will give me 150 pi. I'm just going to keep that in terms of pi to solve the sphere. So the sphere, or the hemisphere, is up here. So I'm going to find the volume of the sphere and then divide it by 2 to get the half of the sphere. Radius is still 5, so 4/3 pi r cubed. My radius is 5, so we do 4/3 pi 5 cubed, so that would be 4/3 pi times 125, which, if we do 125 times 4, 500 divided by 3 gives us 166.6 repeating. So that's the volume of our sphere. If I cut that in half, to get our hemisphere, That'd be our 166.6 repeating, divide by 2 gives us 83.3 pi. So I'm going to add those two together to get my volume. So the volume of the silo shaped thing, we're going to get 150 pi plus 83.3 repeating pi will give us 233.3 repeating pi as an exact answer. Oops. So we'll just do the 83 point plus 150 times pi, and we get approximately 733 cubic meters for our volume. Our second example here, this is a prism with a cone cut out of it. So the volume of our prism is the area of the base times the height. So our base is just a square, 6 by 6, so that's going to be b is equal to 36, so we got that part. Our height is also 6, so times 6, 36 times 6 is 216. So we got the volume of our prism, and we're going to cut out or remove the volume of the cones. The volume of a cone equals 1/3 pi r squared h. Our radius is actually 2 because it gives the diameter of the cone a 4, so r equals 2. And the height, since the cone starts at the top and goes to the bottom of the prism, is also 6. So we can plug those in. 1/3 pi times 2 squared times 6. Alright, so working that out, so that's going to be 4 times 6, which is 24, so 1/3 pi times 24, or 8 pi. 24 divided by 3 is 8, so 8 pi is our exact answer. Our approximate answer would be 25.1. So to get my final volume, we do 216 minus 25.1 we found. Get 190.9. Approximately. And those are cubic centimeters. And that's our compound volume. So just adding or subtracting two three-dimensional shapes. Okay. Last thing we're going to talk about is the square cube law. And the square cube law is really just thinking about how, as we increase in size, what happens to our surface area compared to what happens to our volume. So what we have here on the left is a cube. It's a 1 by 1 by 1. So the height is 1 meter. The surface area is, well, surface area of one face, we should say, is 1 meter, 1 by 1. And the volume, 1 by 1 by 1, so is also 1 meter cubed. Okay. What happens if we scale that up by a factor of 10? So we make it 10 times as tall. Well, okay, so we've made it 10 times as tall. Okay, right here, it's now 10 meters. 10 by 10 by 10. What happened to the surface area? Surface area is now 100 times as big as the original surface area. Okay? It's 10 squared times as big. So the surface area is the scale squared. The volume is even bigger. It's 10 by 10 by 10 times big. So it's the scale to the third power. It's 1,000 times as big. This actually causes problems when you scale up things from model size to full size. Your surface area is your structural, what you can use to hold up your shape here. It grows by 100 times, but your volume, which is what your thing is actually going to weigh, increases by 1,000. So your volume is increasing way faster than your surface area. Okay? And that works for any scaling up. So if you have an object, a 1 to let's say 1/5 sized object. Okay, so we're going to scale up by a factor of 5. Okay, so height, start at 1. Okay, new height. So over here will be our scale size, or here will be our full size. So height increases by a factor 5. Okay, it's 5 times as big now. Okay, what happens to our surface area? Starts at 1, but now it's going to grow 5 squared as big, or 25 times as big is the surface area. The surface area is going to be. About your volume. Volume starts at 1. Your volume is going to increase, not squared, by a power of 3, or 5 times 5 times 5, which is 125 times as big. So your surface area, if we have something scaled down by a factor of 5, when we go to full size, the surface area increases by 25 times as much. The volume increases by 125 as much. So, I said this can cause problems when you're trying to model things. They don't scale up equally. So how something looks and feels at scale when you go to full size will not be the same thing. So this also causes an issue with being able to actually, biology being able to grow very big. So we as humans are limited. We're not going to be able to, you wouldn't be able to grow a human that was 100 feet tall, just because our surface area would grow slower than our volume, which is related to our mass. So we would grow, we would get way too heavy and not have enough surface area to support ourselves. So that's the end of this video.